Jai Shri Ram. My name is JK. I'm working as a assistant professor in the Department of Electronics and Communication Engineering at Vivekananda College of Engineering and Technology, Puttur. So I'm going to explain the Fullwave Rectifier circuit with and without filter. So as you know already, this rectifier is nothing but a circuit which converts an AC voltage into a pulsating DC voltage. So in a rectifier circuit, it consists of two types. First one is half-wave rectifier and second one is a full rectifier. So I'll be explaining about the full rectifier circuit, that is without filter. So as you can see, the diagram of the full rectifier circuit. So we have the first component, which is step-down transformer. So step-down transformer has a two sides. First is this side is a primary side and this side is a secondary side. So the supply voltage of 230 volt will be given to the primary side, which will be stepped down to 12 volt voltage, and there will be 3 points here. First 12 volt point, 0 volt point and a 12 volt point. So the first 12 volt point, the 12 volt voltage will be given to the diode, which is named as D1, and it is given to the anode part, and the one more 12 volt, the voltage from the another point, that is 12 volt, will be given to the diode D2, which is given to the anode terminal. So the cathode point of the D1 and D2 will be connected together, and from this point a load resistor will be connected. So the value of the load resistor will be 1 kilo ohm. So and the other end of the resistor will be connected to the 0 volt line, 0 volt point. So the working of the full rectifier is, so during the positive half cycle, so diode D1 will be forward biased, which means the current will flow through this line and it will flow through the resistor, whereas diode D2 will be reverse biased, means it will be an open circuit, so current won't flow through here. So during the positive half cycle of the input, as you see from the waveform, during the positive half cycle of the input, we get a positive output. So during the negative half cycle of the AC, diode D2 will be forward biased, means it acts as a closed circuit, and D1 will be reverse biased, which will act as a open circuit, which means there is no connection between the input and output. So the closed circuit is formed like this, means the current will flow through the diode D2 and it flows through the load resistor and back to the ground point. So a closed circuit is formed here. So during the negative half cycle input, we get a positive output. So Fuller rectifier uses a complete cycle of the waveform. So whereas in half-wave rectifier it uses only one cycle, means either it can be a positive cycle or it can be a negative cycle. But in the Fuller rectifier it utilizes both the cycle, means it uses both positive and negative cycle. So efficiency of the Fuller rectifier will be more compared to the half-wave rectifier. So as you can see the circuit here, so the supply voltage, main supply voltage is given to the primary side of the step-down transformer, and on the secondary side you have 3 points here, 12 volt point, 0 volt point and again 12 volt point. So this 12 volt, from the starting of the 12 volt point, will be given to the anode of the diode, and the another 12 volt point will be given to the anode of the second diode, which is D2. So this is D1 and this is diode D2. So the name of this diode is D1 and name of this diode is D2. And the cathode of both D1 and D2 is connected together, and from this point a resistor is connected. So the other end of the resistor is connected to the 0 volt point. And in order to see the output and in order to measure to get some of the values from the waveform, we need to connect a probe, which will be connected to the oscilloscope. So one end of the probe will be connected to the point where the two diode and the resistor meets, and the other end of the probe will be connected to the other end of the resistor. as you can see the waveform, I have said already that in the Fullwave rectifier circuit, even for a positive half cycle and for a negative half cycle, we get a positive output. So from this waveform, we need to find out the maximum voltage in order to find out the efficiency value and also to find out the ripple factor. So in order to see the maximum voltage value, click on the measure button, and you can see here measure on is off. To make it on, to the side there is a button, and click on this button. Now it is on, and note down the maximum voltage value. Okay, and after noting down the maximum voltage value, find out the value of VRMS voltage, that is the V suffix RMS is equal to Vm by root 2, and next find out the V suffix DC voltage value, which is equal to 2 times Vm divided by pi. So this is also the value for full load voltage, and then calculate the ripple factor using the formula square root of V suffix RMS square divided by V suffix DC square minus 1, and then find out the efficiency of the Fullwave rectifier circuit, that is for without filter, using the formula V suffix DC square divided by V suffix AC square multiplied by 100. And at last, find out the percentage of regulation value. Formula is no load minus full load voltage divided by full load. So as I already said, this full load the value of the full load voltage is nothing but the same as that of V suffix DC voltage value. And in order to find out the no load voltage value, remove this, disconnect this resistor, and measure the voltage across these 2 points. Okay. You have to remove this resistor. You have to remove this resistor, and one end of the probe will be connected to here, and other end of the probe will be connected to this. Okay, and measure the output voltage. So whatever the voltage value you are getting after removing that resistor, that is nothing but the no load voltage. Okay. Next we will see the Fullwave rectifier with the filter. So as you can see here, there is a fluctuations, or there is a ripples, what you see here. Like it is not we are not getting a constant DC, we are getting a pulsating DC, or you can say it as a ripples. So in order to get a constant DC, almost constant DC, we need to connect a filter. We need to connect a filter, which is nothing but a capacitor, across the load resistor. So capacitor will be connected in parallel with the load resistor. So I've already rigged up the circuit for the Fullwave rectifier with the filter. So the only changes is a capacitor is connected in parallel to the load resistor. That's it. And the rest of all the connections are same. So the first 12 volt point will be given to the anode of the diode D1, and this. And the second 12 volt point, 12 volt line will be connected to the anode of the diode D2, and this the 0 volt line will be connected to this point, to the other end of the resistor. Okay, so to this point. Next, in order to see the waveform, one end of the probe will be connected to this point, that is to this point where the capacitor, resistor and the two diode meets this point, and and the other end is connected to the other end of the resistor. Next, I'll switch on the transformer. So as you see that there are no ripples here, but there is a small amount of ripples here, but not as much compared to the previous one. So we are once again we are not getting the constant DC. So from this particular waveform, you can see there is a small ripples here, and we need to measure the ripple voltage. So in order to measure the ripple voltage, click on the measure button, and since the measure all is off, make it on, and then as you can see here we have maximum voltage, minimum voltage, and V peak to peak voltage. So this V peak to peak voltage is nothing but the ripple voltage. So note down that value. Note down that value. So note down that value, and after noting that this peak to peak ripple voltage value, find out the RMS value, and along with the ripple voltage we need to note down the maximum voltage, which is nothing but V suffix m. Okay, so formula to find out the value of the RMS voltage value is VR peak to peak divided by 4 into root 3 plus VDC, and the formula for finding out the V suffix DC value is Vm minus VR peak to peak divided by 2. So after finding out the value of RMS voltage and the DC, the output voltage, calculate the ripple factor using the formula V suffix RMS divided by VDC voltage minus 1, and find out the efficiency value. Neta is equal to V suffix DC square divided by V suffix AC square. V suffix AC, the V suffix AC value is nothing but the VRMS value multiplied by 100, and then find out the percentage of regulation, which is no load voltage minus full load voltage divided by full load voltage multiplied by 100. So the full load voltage value is nothing but the output voltage value, that is V suffix DC value, and in order to find out the no load voltage value, you have to disconnect this resistor. That's it. Remaining all the circuits will be same. Only you need to remove this resistor, and you have to measure the output voltage across the capacitor. So the voltage what you are getting across the capacitor is nothing but the no load voltage. So, and after getting the no load voltage value, find out the percentage of regulation. So this is about full rectifier circuit with filter. Thank you.